Okay. So the homework assignment that's due on Tuesday the 6th. Is that true? Tuesday the 6th? Man, time's really flying. Thursday? All right, hold on a second. Let's double check here. So the homework's due on Tuesday, and then we'll have a quiz on Thursday. In the introductory assignment, several of you made the same suggestion that it would be useful to you just to get a feel for what the questions look like and get a feel for what my style is like as an instructor if I were to post a sample exam online. So I've done that. It kind of broke my heart to do it because it means I can never use those questions again in a test, and I picked some questions I really like. So it's like saying goodbye to these questions forever.
You can still use them.
Can I? It's generous of you. All right, so here you can take a look at, usually for our exams, there will be 3 questions. Sometimes there would be 4 questions, but what I'd do is instead of having 3 longer questions like this, I'd have 2 longer questions and then 2 shorter ones. But usually it's 3 pages long, the exam, and you'd have 75 minutes to complete the exam in class. And so you can see on this one what I've done is I've kind of, if it's worth 20 points, I'm kind of breaking out where the points are earned. So, if you only do part of the question, then you get part of the credit. And so there you have it. There's a sample exam online. You can look over it and get a feel for what to expect for the tests. So that's there. If you have other suggestions on things that you think would be like a useful learning tool, please let me know because I'm more than willing to consider it.
Formula sheet. Did we get one with the test?
Yeah.
Should we get that posted?
Mm-hmm. Yep. You bet. Yeah, I've gone back and forth as far as formula sheets. There have been some semesters when I've let you prepare one. There have been other semesters when I've prepared it. I'm going to have to think back on which I think has gone best, but I'll definitely get that to you in advance. If it's going to be a sheet that I provide, I'll give it to you in advance. All right, so today we're going to be talking about vapor pressure and hydrostatics. And what's going on in this picture? What are we looking at? Boiling water, right. And in this case, it's boiling water because heat was added. And it doesn't seem like that's something that should need to be clarified, but actually there's more than one way to boil water. It just happens that in this case, the water was heated to get it to boil. Why do you have to heat up water before it will boil? Why won't it just boil at room temperature? Are there other things that will boil at room temperature? What's an example of something else that would boil? Like if we had a liquid, just a container of it, sitting in this classroom, what would boil at room temperature? Propane, butane, right. Yeah, those are liquids when they're compressed, but they want to go into the vapor phase if they were at our normal room temperature and pressure. Water, though, it will go into the vapor phase. When I say phase, there are 3 states of a fluid like water. It can be ice as a solid when it's below 0 Celsius. It's water within a relatively narrow band of temperatures from 0 to 100 Celsius. And then after 100 Celsius, the water wants to become a gas. And so that's what's going on here is that the water has been heated up to a temperature where it wants to be in the vapor phase. Now, of course, we know that even if you don't heat water, if you just leave a pan of water out in the classroom, even at room temperature, some of it will evaporate. So if you want to stick around with me as an instructor all the way to hydrology, CE 433, I'll explain evaporation to you. Maybe before that, but today we're just focusing on boiling, which is like a much faster version of evaporation where a greater number of the water molecules are going through that transition from liquid to vapor. So at sea level, water boils at 100 Celsius. At Mount Everest, water boils at 69 Celsius. Is it something about the water over there? Why is it that water boils at a different temperature at Mount Everest than it does in Mount Huntington? The pressure. Elaborate. The pressure what, where?
The boiling point of water raises with higher pressure and then lowers at low pressure.
Okay, so the boiling point isn't fixed. It's a function of the surrounding pressure. And this, what we can't see in this container of water is, here's the water, but there's other stuff around it. There's air surrounding that container. And so, you know, the water, the molecules in that water, they want to escape. Some of them have enough kinetic energy that they want to be liberated from the liquid phase and they want to become vapor molecules. But the air pressure is usually so high that those molecules can't escape because the air pressure is greater than the vapor pressure. And the phrase vapor pressure is a description of basically how much kinetic energy on average the water molecules have. And it's the kinetic energy, their movement, that allows them to eventually escape from the liquid phase to the vapor phase. So there's the liquid state and the vapor state. When we heat water, we increase the vapor pressure. So it's like we're making these lines longer. By heating the water, you increase the vapor pressure so that it can escape that pressure of the air. And it's not like there's actually a boundary there. It's just that in order to join the pressure of the other gases, you have to have the same pressure as the other gases. You know, you can't, it's like going against traffic. You have to, you know, in the case of traffic, have the same direction to be able to flow. In this case, the water has to have as much pressure as the surrounding gases to get into it. So the idea about Mount Everest is that different places on the Earth's surface, if you go up in elevation, the pressure of the atmosphere decreases. And so if this pressure that's acting downward against the water, if it's decreased, then you don't need as much heat to increase the vapor pressure to the point to where boiling will occur. All right, so let's watch a little video. Oh, hold on, where's my link to the video? Oh, okay, it's on this next slide. By the way, are there any questions about this before we move on? All right, so the term vapor pressure is the pressure at which a liquid will boil. And vapor pressure goes up as the temperature increases. And here's a table that illustrates that effect, that temperature dependence. And it says that when water is cold, it has very little kinetic energy. There's very little molecular movement. And so there isn't enough pressure within the liquid to get out into the atmosphere. But at 100 degrees Celsius, there's an equality between the vapor pressure of water and the atmospheric pressure. You know, this is measuring the pressure in terms of millimeters of mercury. And if you remember back from chemistry, one atmosphere is equal to 760 millimeters of mercury. So at 1 atmosphere, the vapor pressure of water, is 1 atmosphere at 100 degrees Celsius. And it's ironic to see that actually there still is a vapor pressure below zero. So ice can evaporate. There is sublimation, which is the direct transfer of water from the solid phase to the gas phase. Here's a graph of this same data. And what it shows is it's a nonlinear response. And so as you heat up the water, the vapor pressure increases dramatically as you approach the boiling point. So At atmospheric pressure, the water will boil at 100 Celsius. The water can boil at lower temperatures if the surrounding pressure of the atmosphere is lower. So let's watch this video. So you got the clue when he put his fingers into the water that it wasn't hot. He was fishing out the pasta in a way that you probably wouldn't put your fingers into boiling water like that. In fact, quite to the opposite, if you let the water to continue to boil over the long term, it would freeze, which is really unexpected. The reason why is that for water to go through a phase change, so for it to go from liquid to vapor, it consumes energy to go across that transition. And maybe in chemistry you remember that you have to add a certain amount of heat to melt a certain amount of ice. You know, like there's a constant. You can look up, you know, how many joules it takes to melt a kilogram of ice. Even though the temperature is from 0 Celsius ice to 0 Celsius water, it still takes some energy to go through that melting process. In the same way, it takes some energy to go from liquid to vapor, just to push it through that barrier. And so the energy comes from the water. And so actually over the long term, that water will get progressively colder and colder and colder as it's boiling, and then it turns to ice. I found another video that I didn't link to that shows that process of they left it in for, you know, several minutes with a thermometer, and you see the temperature decreasing until it starts to form ice crystals. But we're not necessarily talking about that phase change into the ice so much as what we were seeing is when the vapor pressure is bigger than the pressure of the liquid. And so the pressure of the air that's surrounding the liquid is very, very low. And so the vapor pressure was greater than the pressure inside that atmospheric belt.
So, like a pressure cooker when you're cooking on the stove,
Mm-hmm.
it adds pressure so you can add more heat without evaporating water.
Very good. That's exactly right. Yeah. So the pressure cooker, what it's doing is it's saying that you're going to cook with a higher temperature than you normally do. Normally, if you're like cooking lentils, you know, what it takes, I don't know, 20 minutes to cook lentils at 100 Celsius, but then if you put a lid on top, and so you're preventing the water from boiling at 100, and so you're forcing the water to boil at a higher temperature, then you're able to cook things a lot faster. So like Instapot and other kind of pressure cookers rely on that principle of increasing the pressure of the surrounding gases so that the boiling point increases rather than decreases. Fahrenheit? Your guess is as good as mine on Fahrenheit. Yeah. But those pressure cookers can be pretty dangerous. Actually, anybody remember the Boston bombings? That's what they used in that Boston bombing was a pressure cooker. So they're designed to hold pretty high pressures. So here's another table that illustrates vapor pressure. This is table A5 in your book. The appendices at the back is where, for homework problems, you can look up the vapor pressure at a certain temperature. And here's just another kind of fun gee whiz. All right. Now, vapor pressure is important in civil engineering, mainly because of the damage that boiling water can do to pumps, pipes, and other engineered structures. And there was a dam, with an emphasis on the word was. There was a dam in Russia, I guess the dam's still there, but the power plant isn't, that generated a lot of electricity. It was a really sophisticated operation, and I don't know the total number of megawatts in the area, but the electricity was used for aluminum smelting. And so the dominant industry in that part of Russia was very closely tied to the availability of cheap and abundant electricity generated by that hydropower. Unfortunately, what happened was the place exploded because there was something called cavitation. And what cavitation is when water is moving very quickly, sometimes its pressure decreases. And we're going to be talking about the Bernoulli equation and why there's a relationship between velocity and pressure. But the main thing that you need to know at this point is that what happened is the water pressure decreased, and in fact the pressure of the water got so low that it began boiling inside of pipes. And when it does that, when these little air bubbles form inside of water, these little cavitation air bubbles can, when they expand again, send a small shock wave through the water, and they can cause corrosion and pitting of pipes. And in fact, there have been some dams in the United States that have been threatened by cavitation. Back in 1983, 1984, there was a really wet spring out in the western part of the United States, and there was, we'll look at pictures later in the semester of a dam that was really heavily damaged because of the same issue of cavitation. So
Is that something that can be prevented?
it can, yeah. It can be prevented, and there's a way of assessing the risk or the potential for cavitation. In hydraulic engineering, what we'll do is we'll go through some calculations where you're calculating what's called net positive suction head, NPSH, and you're trying to look at like what's the risk of cavitation, and if you get kind of close to the threshold of having that risk, then you choose to construct with different materials. Maybe you have to armor concrete or use a smoother pipe that won't be damaged by the pitting and corrosion that those little shock waves can cause. And ironically, cavitation, they're just tiny little bubbles of gas. You know, when water is boiling, it's just a few molecules at a time that are going into that vapor phase. And so it doesn't take a huge explosion to do something like this. It starts off as a little bubble, but that little bubble sends a shock wave through the water, and it's enough to put a little crack in the pipe or to chip away just a small amount of steel. And then another bubble comes along and it chips away a little bit more of the steel, and just progressively and gradually over the course of days, weeks, months, maybe years, then there's enough damage that then it can fail in a really catastrophic way. So it's not the sort of thing that we can't predict and can't prevent. You can, but sometimes cavitation occurs in unexpected places when just the right combination of events happens. So that's why this disaster in Russia occurred. So I show you the picture just to illustrate that we'll come back to talk about vapor pressure both this semester and also next semester. It's a really important issue. The main thing you need to remember is why water will boil when no heat is applied. And it's just when the pressure goes down. When the pressure of the water, or when the pressure of the air that's surrounding the water is less than the vapor pressure. And that vapor pressure, remember, you can look up in your book, it depends on temperature. It's just the warmer the water is, the more likely it is to go into the vapor phase. Okay. So I showed you this slide in class previously before when we were briefly talking about pressure. Pressure intensity is usually just called pressure, and the units are force per area. So a Pascal is a Newton of force over a square meter of area. That's a Pascal. And pressure acts in all directions equally. It doesn't have magnitude, it just has it doesn't have direction, it just has magnitude, so it's a scalar. And you saw right through this trick question I was going to ask about which has most pressure at the bottom, and someone correctly mentioned that it only depends on how deep the water it is. It doesn't depend on how wide the body of water is. The pressure at the bottom is dependent on your depth. So the hydrostatic equation is the formula that we use to quantify that. If we have a tank of water, and let's just say for a starting point, we measure our elevations relative to the bottom of the tank. Our elevation datum is here at the bottom of the tank. And we go up some distance and we get to the surface. At the surface of the interface between the air and the water pressure is the same as the air pressure where they touch. But then when you go down below that interface, the pressure is gradually increasing, and it's increasing at the rate of gamma. So gamma is the unit weight of the fluid. And gamma, does anybody remember the units of gamma? Gamma has units of newtons per meter cubed. So what we're talking about with unit weight is how much weight is there in a certain volume of water. So the hydrostatic equation says as you go down through water, the pressure is going to increase a certain number of newtons per meter squared per meter of depth. So newtons per meter squared per meter. So water, for instance, the typical unit weight for water, unless we're given some temperature specifications, the general is 9810 newtons per meter cubed. So what that means is if you go down through water, dP dZ is negative gamma. Okay, now the negative sign there is just that when you go down through the water, the pressure increases. If you go up through the water, the pressure decreases. And so the direction is opposite. This Z datum, if you're going up in Z, then the pressure is going down. So that's why the negative sign is there. But now the rate, what it means is if you go down 1 meter in water, so for 1 meter of depth, your pressure increased by 9810 pascals for every meter. And it's a linear response too. If you go down through a meter of water, it doesn't matter if it's the first meter or the last, that increase in depth is going to give you the same increase in pressure, regardless of which meter of water you're traveling downward through. So this is the hydrostatic equation. This is a really important one. Although we don't use this form of it as often for solving equations. We have some other variations on this hydrostatic equation that it's generally more convenient to use for problem solving. But consider the units and make sure that you understand why newtons per meter cubed, why that's a rate. It's a rate of pressure accumulation because newton per meter squared, that's pascals. So what we're saying is gamma is the same thing as pascals per meter. As you go down through a meter, the pressure is increasing by 9810 pascals. Okay, so assuming uniform density, so that means if you're going down through a fluid that's just a continuous body of that same fluid, it's not like you're going through different types of fluid. So assuming continuous density, then we could integrate this hydrostatic equation to get piezometric pressure. Okay, so we rearranged this, and piezometric pressure is saying for a certain location where you're keeping track of your elevation, Z, above a datum, then the pressure plus gamma Z is equal to this P sub Z, piezometric pressure. And you can rearrange piezometric pressure by dividing each term by gamma. And piezometric pressure can instead be expressed in terms of piezometric head. And the hydrostatic equation says that piezometric head is constant in a fluid. So between 2 points that are inside of this fluid, if this is a liquid, and we've got 2 locations that we're interested in, what this equation means is that if you go down, then your Z is decreasing, but this first term of pressure head, it's increasing by the same amount. So there's an exchange between elevation and pressure as you go through the fluid. Now what happens if you go, so I drew this little line here. If we go down, the pressure is increasing. But what about if you go sideways? What's happening to the pressure then? There's no change. Yeah. It's just as you go upward and downward vertically through the fluid that you experience a pressure change. So we can rearrange this original this original hydrostatic equation, and this is the form of the hydrostatic equation that we'll use more frequently. And what it's saying is that pick 2 points of interest. If you know the pressure at one of them and the elevation at both, then you can calculate the pressure at the other location. So we've got 4 variables here. If we know 3 of them, we can predict the 4th. So let's put that to practice. Let's say that we have a tank of water here, and we're measuring some elevations according to a datum. Maybe it's the bottom of the tank, maybe it's sea level. It doesn't really matter. We've got some datum, and we're measuring our elevations to both 1 and 2 from that same datum. We know the pressure at 1, and we want to find what's the gauge pressure at 2. All right, so we first look at what data we have. At 1, we have the gauge pressure. So what I'd like you to do is, hopefully everybody brought their calculators today. See if you can calculate P2 using this hydrostatic equation. First of all, calculate it in terms of the gauge pressure, and then on part B, I ask you to find the absolute pressure. So I won't remind you quite yet how to convert between the two, because I want to see if you remember. But we will go over it in just a minute. Okay, so I have the solution up there on the screen if you want to check to make sure you're headed in the right direction here. So what we're starting off with is this hydrostatic equation that says the pressure head and the elevation head at one location is going to equal the pressure head and elevation head at the other location. That's how we would, in words, describe that hydrostatic equation. So what we need to know is the elevation at both points of interest. So at location 1, the elevation is 34. At location 2, the elevation is 26. We need to know the pressure at 1, and I'm noting here that that's the gauge pressure, which that means the gauge pressure is we're assuming the water, that the Earth's atmosphere is 0. So we're using the Earth's atmosphere as our basis or our starting point for measuring pressure. So rather than just starting to substitute the numbers in directly, what I did was algebraically rearrange things to solve for P2. So here's what the equation looks like if we're going to solve for P2, and then substituting in the numbers from there. We've got the pressure head at 1, the elevation head at 2, and we're subtracting out the elevation at 1, subtracting out the elevation at 2, and multiplying all that by the unit weight. So it should be that the gauge pressure at 2 is 144 kilopascals. Who also got that same value? Okay. It's always good to see that the numbers work out. That's the gauge pressure. How do we find the pressure absolute if we know the pressure of the gauge? It's P gauge plus the atmospheric. Very good. And what's our typical atmospheric pressure in terms of, like in this case, where we're, like I've expressed it so far in kPa, 101.325 kPa is kind of the standard atmospheric pressure. So once you have the gauge, and what it did is it said, what's the absolute pressure at 2? So absolute pressure at 2 is the gauge pressure plus 101.325 pascals. Okay, I'll give you a minute to finish writing that down if you're still copying or still doing the calculations there. So this is exciting news, right? Now you can know what's the pressure at the bottom of the swimming pool. You just measure how deep it is, multiply it by the unit weight, and that's how much the pressure is at the bottom of the pool. Like you could know how strong your ears are. You can see at what depth does it start to bother your ears, and then therefore you can equate it to a certain pressure. Anybody here ever do scuba diving before? A few of you? It just seems dangerous. I don't know. We don't belong down there, you know? It's not like fish show up where they don't belong. All right.
There's whales on the beach all the time.
Yeah, and are they alive? Yeah, briefly. All right. So here's the full version of the hydrostatic equation. We can always use this, but sometimes it's convenient to just express the hydrostatic equation in terms of a change in pressure. So I kind of hinted at this when I said, well, all you have to do is know the depth of the water of a swimming pool and the unit weight. So the change in pressure between 2 points is delta H, which is the vertical depth, multiplied by the unit weight of the fluid. So if you go down, the pressure is increasing. If you go up, the pressure is decreasing. So here's an example. This Challenger Deep, that is the deepest point in the Pacific Ocean. It's off the coast of the Philippines in the Mariana Trench. Some of you, I think, looked up the pressure at the bottom of the ocean, right? You probably find that in lots of different sources, but let's calculate it. If the depth there is 10,911 meters, and it's seawater that we're talking about, so the unit weight of seawater is a little bit larger than fresh water because of the dissolved salts, 10,100 newtons per meter cubed. So what this abbreviated hydrostatic equation says is that the difference in pressure between the surface of the ocean and the bottom of the ocean, delta P, is delta H times gamma. So it's 10,911 meters of depth, 10,100 newtons per meter cubed. So the pressure down there is 110 million 201 100 pascals. That's the change in pressure. Just as a point of comparison, do you know in the water network that we have here in Huntington, what's a typical water pressure for a municipal network in terms of pascals? I mean, you maybe have no idea in pascals. Maybe you know in PSI. I don't know in PSI, but I do know in pascals. The typical range is that you may have from 240,000 up to maybe 850,000 pascals in a water network. So what this is saying is we're not even at 1 million, but at the bottom of the ocean, the pressure there is 110 million. So it's a lot of pressure. That would make your ears hurt. It would probably squish you into a little cube. All right. Any questions about this abbreviated hydrostatic equation? Yes?
For a specific weight, and I could look at 10,700 or 10,007.
Yeah, it depends on temperature. Yeah, so if you're working a homework problem and you use that value from the back of the book, that's fine. This just must be for some other temperature that I looked up. Yeah. Okay, so what if we have two liquids on top of each other? What if we have a layer of oil on top of a layer of water? Okay, what I'd like you to do is calculate the gauge pressure at the bottom of the tank. I've given you here the specific gravity of the oil, the thickness of the layer of oil, and then the total level of liquid in the tank is 4 meters. So I'd like you to Get out your calculators and calculate at the bottom of the tank here, what is the pressure? Here's the hint. You have to go one liquid phase at a time. You have to go from the surface, which is an interface of a gas and a liquid. So you go from the surface down to where the oil and the water meet. So you do that one step, find out what the pressure is at the interface between the two. And then you go the rest of the way down to the bottom. There's going to be two different unit weights. So the pressure is cumulative. Like there's an additive relationship. As you continue going down, the pressure continues increasing. But you can only apply this hydrostatic equation when you're going through the same fluid. You couldn't go all the way from the top to the bottom in a single calculation step, because then which gamma would you use? You've got two different gammas. So the solution to that is you have to do it one step through the oil and another step through the water. That's the hint. Okay, so I've on the sketch here, I've labeled points 1, 2, and 3. And by the way, it's not really a trick, but you have to get accustomed to using the dimensions that are given and converting that to the dimensions that you need. So it said there's a 1.1 meter depth of oil, and the overall liquid is 4. So then that means the water thickness is 2.9 meters. So just because I said 4 doesn't mean that the water depth you should put in there is 4. You sometimes have to just look at the information you're given like in a neutral way and make sure that it ends up being what you need. So if we're going to use the hydrostatic equation, we need to have the gamma of both the water and the oil available. And so by multiplying the specific gravity by the unit weight of water, we can get the unit weight of oil. So 7357.5 newtons per meter cubed. And now we just do a counting. It's like bean counting from here on out. Anytime you go down, the pressure is increasing. So P2 is whatever pressure there was at 1 plus the difference between the 2 points. So the difference between the 2 points is an increase in the amount of the depth multiplied by the gamma. So it was 0 pressure at location 1. The depth is 1.1 meters through the unit weight of oil. So we know the pressure at 2 should be 8,093.25 newtons per meter squared. So far so good. Any questions? So now we're at 2. Like if we put in a pressure probe right at this depth where the oil and the water are touching, that's the pressure it would be. And as we continue to go deeper, the pressure is increasing. But now it's increasing at a different rate because we're moving through a different fluid. So that's why we have to use a different gamma for this next part. Is we'll set up this equation. We're saying the pressure at 3 is the pressure at 2 plus the change. And the change is the depth and the unit weight of whatever this new fluid is, in this case water. So it's going to be the pressure that there was at 2 plus the change. And so the overall pressure at 3 should be 36,542 pascals. I see some heads nodding. I think you got the right idea. Any questions about this example before we move on to one that's slightly more complicated? All right. Okay, our last example for the day before we take a look at some key ideas from homework problems. Well, what if we have 3 fluids? We combine all the ideas here. I tell you the specific gravity of an oil, and then the density of water, and then the unit weight of this last fluid is not known. So actually, we're going to use the change in pressure to be able to calculate what is the unit weight of this last fluid. This is a new example, so if you're flipping through your lecture notes wondering where it is, this is a bonus. You're getting more for your money this semester than the guys last semester got. Good. I can tell you're excited. All right. So what I'd like you to do is find out what is the gamma of this purple fluid. The same procedure that I followed before. My suggestion is that you start off by numbering the layers. You know, maybe we'd call this first, the air-water interface is 0, then here's 1, 2, and maybe 3 is that dashed line. That's the depth. But I'm going to stop this recording. I'm going to stop talking and give you a chance to collaborate with your classmates and calculate what's the unit weight of that fluid. And this is the type of question you could expect to see on a quiz. You know, I've already posted the sample exam online, but I think this is a quiz strength question where in 7 or 8 minutes you should be able to solve for the gamma of the fluid. All right, I was very gratified with what I saw. So we started off with the pressure of the air is 0 if we're measuring the pressure relative to the air. And so I called that layer 0. Then at interface 1, which is where the oil and the water touch, to find the pressure there, we have to first of all know what's the unit weight of that oil. And since this oil was a slightly different specific gravity than the last example, we have to calculate a new unit weight. So at 7651.8 newtons per meter cubed. And remember, I'll make the commitment to always write my units in every example I work. And I do that not because it's fun to take the extra time, but I just think it's a good habit to be in. So I'm trying to set a good example for you. Although my reflex is the same as yours, do things as quickly as possible with the least amount of effort possible. It's worth putting the units every single time. So that's why they're there. So we're going down 0.5 meter through this oil. The pressure at 1 is 3825.9. Then I have this statement, the pressure at 2 is the pressure at 1 plus the difference. And so there's a certain amount of increase as we go down through this water layer. And I saw that almost everyone was able to eventually figure out that, you know, if you've got some special temperature of water where instead of 1,000 kilograms per cubic meter, which is our usual just default value, what we've got here is 999 kilograms per cubic meter. And so we need to convert that to a unit weight just by multiplying by G. Because remember, the whole definition of gamma is rho times G. So it's density times gravitational acceleration in order to get the specific weight. Okay, so we got the specific weight of the water layer, and the net pressure at 2 is going to be however much pressure there was at 1 plus the increase. So that's 19,016.2 kilonewtons per meter squared. And then finally, this last step, what we say is, well, we know the pressure at 3, and the difference between 2 and 3 is this delta P, and so the delta H that was responsible for the increase in pressure, if we put in the delta H and the delta P, then we can calculate the gamma. And so in a way, we can find out the unit weight of the fluid by measuring the pressure difference some depth into the fluid. So the unknown here wasn't what's the pressure at depth, but it was rather what's the unit weight when we haven't observed pressure at depth. Any questions on that example? All right. If you need to take a second look at any of these examples, of course, remember that the videos are posted on YouTube. Let's look at some key ideas from the homework that you've got coming up. Okay, this problem 67. What it is there's a ring that's a circular ring, and this diagram is just a cross-sectional view. And you're trying to use this ring to quantify the surface tension constant for the fluid in question. And we know the mass of the ring, we know the inner and outer diameters, and we know the force, how much we have to pull it up, because the water is continuing to hold on to this ring. So from a top view, this is what the ring would look like. So we've got the inner and the outer diameters. And so the surface tension equation, remember, it says the surface tension constant times some length parameter is how you find the force. So you're given this force, they express it in terms of a mass equivalent. You already know how to convert between mass and force, right? It's just multiply by g. And that will enable you to go from grams to newtons. But the length, there's two lengths that are important here. There's the inner circumference and the outer circumference. And it's both of those together that's responsible for this force that you have to pull upward to get the ring out of the fluid. So I just wanted to point out that this length is the sum of the inner and the outer circumference. And what's the formula for circumference? Pi d, right. You know, in math, you do a lot with radius, but for whatever reason, in like fluid mechanics and hydraulic engineering, it's just more common for us to express things in terms of the diameter rather than the radius. And I guess because if you're out in the field measuring a pipe, it's just easier to measure from outside edge to outside edge and say, well, here's the diameter, than trying to estimate where's the center and then hold your tape measure up to some center point that doesn't actually exist on the pipe. So it's easier to measure diameter. I guess that's probably why we use it. Here's another problem. This is saying that we have a mountain, and we know from what we talked about today that when the atmospheric pressure is 101 kilopascals, that the water boils at 100. And this problem says that up at an elevation of 3,000 meters, where we're given a certain atmospheric pressure, what is the water going to boil at? And they give you an equation. This equation is called a lapse rate. And a lapse rate tells you how much the atmosphere cools with pressure change. And so you can use this to find out the vapor pressure for a given temperature. But I just wanted to point out that the delta P per temperature change that they've given you, you're going to have to try and calculate what the water boiling point is by finding the change in pressure between the 2 points that is based on the change of elevation, and then you can find the change in the boiling point. So sometimes it helps to visualize, like where the variables apply on the drawing. Sometimes sketching the given information onto the drawing itself will help you to see that. Okay, so that's all for today. We're out of time. Let's just take one last look at these announcements here. So you've got homework due on the 4th, so that's Tuesday, and then on Thursday we'll have our first quiz.